the mic on? Can you hear me? Yeah. Okay, let's get started. So how'd the exam go? Was it hard? Yeah? It was obviously based on Lab 10, right, which you should have gotten back before the exam. Sometimes students don't immediately sort of assimilate thinking in terms of objects. It can be hard at the beginning. We're going to do one more homework where you work with objects, so it should be easier the second time around. We're going to start that material today so you can see what it's like. But we'll try to get the exam graded as quickly as we can. So we'll be grading exam 3 this week. I still have to scan it. I just got back late last night. I still have to scan the exam in, and then I'll talk to the TAs, and we'll be starting the grading then. We'll take Lab 11 tomorrow as usual. You guys feel like you need a day off from labs or not? Yeah? Would it help? All right, fine. Let's skip Lab 11. He's laughing in the back. All right, we'll skip Lab 11. I'll post it today. To be frank, I haven't written it yet, so it's easy for me too. We only have 9 lectures left, so 3 weeks. So that leaves us at, if we skip 11 today, it leaves us to 12 labs, which is a nice round number. So we'll take a day off from lab. Questions of the day, we'll start again. Start again on Wednesday. I got to get a new clicker. Question days will resume on Wednesday. And we'll start grading homework 2 right after we're done with grading exam 3. Okay, so I was thinking on the way back from the wedding yesterday what I would like to do for the rest of the term. There's only 9 lectures left. I would like to give you one more short homework. And I want it to be a little bit different than the things we've done before. So I've decided I'd spend the rest of the term talking about working with text. And we'll do an object-oriented homework with some text mining kind of ideas built into it. Now, normally this kind of stuff is not done. You would never code this stuff yourself. There's some wonderful libraries that do all this for you. But the interesting stuff that happens is happening inside those libraries. So we're going to take a little bit of time for the next few lectures and try to work through how we might deal with text ourselves if we were writing the library. And then when you get around to the homework, haven't decided exactly if we'll use a library or if we'll have you extend what we do in class. But it'll be something along the lines of what usually is done with a library like TextBlob or NLTK, the Natural Language Toolkit. So we're going to work with War and Peace and Treasure Island because these are easily found public domain texts. And we're going to do a very simple thing. We want to know what are the 20 most commonly used words by each author, Robert Louis Stevenson and Leo Tolstoy. Now, this is the kind of thing where with the natural language library, once you read in the book into Python, it's like one command, top K, and out pop the 20 top words used in the book. But doing that actually is kind of interesting. So we're going to do that a little bit at a time. The second thing we're going to do is we're going to detect who are actually characters in the books. We're going to be dealing with fiction here. So typically it's a story about individual characters. So we're going to identify words that represent characters, and then we're going to map the interactions between those characters and try to draw a picture of what's going on in the book. We're going to do it all with a few Python commands. So you open a book, read it, and out pops a character map that tells you here's how the interactions of the characters work. And then we'll do some fancier stuff. We've done, in the past, we've built these embeddings, these graph embeddings of the characters. So you identify the characters of the book, and then you plot a graph where each node corresponds to a character, and you draw the interactions between them, and you can like pick up a character and drag it across the screen, and you see how the other characters follow and so on. Don't know what, we'll figure something out that's interesting. So I downloaded the 2 novels in plain text from Project Gutenberg, which was a project at the University of Illinois Libraries that was meant to digitize texts of publicly available books so people could have them. These are actually pretty interesting if you ever want to browse Project Gutenberg. There's some front matter in each text that you can strip, but otherwise it's just a plain text representation of the book. So Treasure Island is about 68,000 words, almost 400,000 characters, and War and Peace is 500,000 words and 3.5 million characters. So they're fairly large. So the first thing we want to do, we would like to be able to get the words out of the text, the individual words, and basically get a list of words along with their word count. So type a command and say read War and Peace, and it opens the file and brings in this file of War and Peace, and then it returns to me a dictionary, Python dictionary, where each word is the key and the number of times that word occurred in the text is the number. Okay, so it's reasonably straightforward. We use this function to read each line from a file. We've seen functions like this before. And we're going to assume that we're only interested in words that are 4 characters or more. Why? Well, there's a bunch of words in the English language that are, they're often called stop words. They're words that are like is, the, it. They don't really add to the sentence. If you drop those words, you could still get the sense of what people were talking about. And they are, of course, commonly, the word the and these words are commonly used in English, so you can imagine their word frequency counts are very high. And secondly, we would like to get rid of any sort of extraneous stuff that goes with the word. So if the word can appear at any capitalization, we'll treat it as if it's the same word. If the word has an apostrophe, like in the possessive form, we'll just strip that off. Any punctuation in the sentence, we're going to get rid of. We're just going to try to distill it to simple words. So here's the first attempt. It's really straightforward. I've read in my text in the big string. So this S is 500,000 words in a string from War and Peace. And I simply create a list of words where I take every word in the lowered version, split version of the sentence, and just throw them out if they're shorter than 4 characters. And this works fine, except I had said that we'd like to avoid words that have like a possessive form. So when you say a student's exam, there's an apostrophe after the S, and we'd like to get rid of that apostrophe. So let's try to get rid of those non-alpha character letters in the word. And we can do this with the command that we've already seen. So let's move. For the start, let's just get rid of things that come after a word, like a question mark, a period, semicolon, or exclamation point. These are tightly nested against the last word in the sentence, so we're going to start with those. We already have a mechanism for dealing with this, just don't know that we have it. And that mechanism is this strip function. So we've seen before taking a string and lowering it, and then taking that lower string and splitting it on words. So the split recognizes blank spaces and separates it into a list of words separated by blank spaces. We've also seen the strip command before, but typically when we didn't provide an argument to strip, it would strip away any white space on either side it would trim away the white space. Here we're telling it trim away any of these characters from the individual remaining word. So the split consumes all the white space between the words and gives us a list of words, but those words still contain any trailing punctuation, which we strip with this special list of characters that we want to get rid of. And this is okay, except the stripping of these characters is done after checking for the length of the word. So a word that appears to be greater than 4 letters, say a 5-letter word, where the last letter is a period, is being included now because the test is applied prior to the stripping. And maybe that's okay because this 4-character limit was just an arbitrary limit to get rid of those simple words. Maybe there's a better way we can think of to get rid of those stop words so that we don't include them in our analysis. And I really want to, I don't want to just read this one line from the file. I'd like to build that dictionary of counts as I go. So I'd like to open the file, read in the text, and as I break it into words and remove the punctuation, I'd like to be updating the dictionary of frequency counts for each word. Now this is really pretty straightforward stuff. At this point in the class, you've done things like this before. Building a dictionary with a dictionary comprehension that counts, or with a accumulation pattern that steps through words that adds one to the dictionary. You've done questions of the day where this stuff is what we have to do. And here's an example of what you might have done. So you pass in a dictionary that is word frequency pairs. You take a string, which you've presumably just read from a file. Maybe you're reading in one line at a time from the file for War and Peace. And you break that sentence into lowercase words. You throw out any words that are not more than 4 characters. You strip off every punctuation, and for every word in that collection of words, if that word is in the dictionary, you add 1 to the dictionary count. If the word is not in the dictionary, you add it to the dictionary because you've just found the first occurrence of the word. And you just do this over and over again for the sentences or for the strings that you read in, and at the end of the day, you return the dictionary. It's pretty straightforward. So let's read the file. So I'm going to start by file name here. It will be either War and Peace or wherever I've stored my text. My dictionary will be initialized to a simple empty dictionary. I'm going to open the file for reading, and we've seen this done in many ways. We've seen with open file. There's all sorts of forms we can do here. But I'm just going to sandwich this loop inside the opening of the file and an explicit close of the file. So I'll open the file for reading. For every line in that file, I will call my parse function that you just saw, passing in the line and the dictionary, which is initially empty. Now remember, this dictionary here is being passed by reference. It's a structure. It's a mutable structure. So when I pass D, when I take the value of D here on the invocation of this function, when I evaluate the argument, I get the value of D. That value is not copied. It is the whole structure of D. And I hand this to the function, and the function will make changes to it. It'll add stuff to it. It'll increment counters. And so the D, which exists at this scoping level here, will be mutated by that function and will continue to grow and collect frequencies. All right? Everybody understands this, right? So when you're passing structures like lists, dictionaries, and so on to a function, if those structures are mutable and the function makes changes to it, those changes are permanent. And they are passed back to the scope that invoked the function. All right? All right, so this is my simple thing. If I do this, I get 24,000 words in War and Peace, and Treasure Island, I get about 7,000 words. Now, I had originally said I'd like to know what are the 20 most frequently used words by Tolstoy and by Robert Louis Stevenson. And how do I do that? Well, I have the frequencies here. For all 24,000 words, I not only know that I have 24,000 words, those are the keys in the dictionary. The values are how many times those words occur. And if I want to find the 20 most frequently used, all I have to do is take the keys from the dictionary, sort them in reverse order of the frequencies that I've calculated, that I've scanned and computed, and then just take the top 20 of them. So I have a dictionary that looks like word frequency pairs. The obvious solution here is just to extract that list. So here's my dictionary. I'm going to take every item in the keys. So remember, dictionary.keys. Keys is a method of dictionary. It returns a list of the keys in the dictionary, which here is just a list of 24,000 words. So for each word in those keys, I'm going to create a list of tuples where I have the frequency of that word, comma, the word. So I had word, colon, frequency in the dictionary. Now I have frequency, comma, word in this list of tuples. So I'm basically converting the dictionary into a list of tuples that reverses these. And that seems like an awkward thing to do. And we're going to talk about how we can avoid doing that in a second. That's where this is going. But now I can use my sorted list, my sorted function, which you've seen before. On this list, I can sort it with the reverse flag set to true. Now let's see what sort does. Sorting a list of tuples, you sort first on the first item, and if the first item matches, you sort on the second item. So this will give me a list of all these tuples where we're in descending order of frequency, and if I have two words that occur exactly the same number of times, those words will be sorted in reverse alphabetical order. Okay, it's just a regular sort. This looks pretty good to me. It'll give me that sorted list, and then I'm just going to take the 0 through k elements of that list, because I've got this top k function that takes a parameter here, which we're going to pass 20, and that'll give me the top 20 words in the list. So, few lines of Python, open a file, read it in, build this dictionary, frequency dictionary, and then sort it and lop off the top 10 k words. So this seems a little bit weird, that I took the value and key from the dictionary, sorted them to get frequency item pairs just to make the sorting easier. It'd be nice not to have to reverse the order. It would be nice to be able to have a list of value frequency pairs, for example, rather than having to build a dictionary, build a list, and reverse things. And there are ways of doing this with sorting. So the sorted function, you knew about the reverse flag. I think we talked about that before. But there are all sorts of other parameters to sort it that can make your life a lot easier. And one of them is a comparison key operator. So I would like to be able to use, so this is a module called operator. There's this function called item getter, which lets me sort of dissect an item and pick out an element of that item. And if I use this with my sorted function, I can say sort on just the second element, or sort on characters 5 through 8 of the words. So when we sort, say, a list of words, we sort them in alphabetical order starting from the first character, and that's great. That's what most people want. But maybe you have an application where it's important that you sort words by the 5th through the 10th characters and ignore the first 5. Well, that's awkward to do with just a regular sorted function. But if I have a way of extracting from the thing I'm sorting just the key part, the specialized key part, I can use my sorted function to in a much more flexible way. So here's what I'm going to do. I'm going to change my top k function, and I'm adding a parameter to my sorted function. So I already had this name parameter reverse, which I set to true, which sorts from high to low rather than low to high. And now I'm going to use this key parameter where I'm going to use this item getter 1. And item getter 1 means, remember, L is a list of tuples. The 0th element is the frequency, and the first element is the word, or is it vice versa? Oh no, we're not reversing the item. So the first item in the tuple will be the word, and the second item will be the frequency. And the key here says take the first element, Python 0 index, first element, which is now the frequency, out of the tuple when you make your comparison. So instead of comparing in order within the tuple, just look at item 1 of the tuple, which is the second item in the tuple, and sort based on that. So the second optional argument lets me a way of using a comparison key from each item I'm sorting. The items I'm sorting are tuples, which are item, comma, frequency. So item getter 1 will be the frequency part. That is the key that will be sorted in reverse order, and I'll get back a list of these tuples sorted from highest to lowest frequency. Okay? So we're changing our function using different features of Python to make it a little bit more understandable. We can do better. Continue to do better. So remember, item 1, this is item, which ranges over the keys in D. And so, item 1, this is what the item looks like. So item 1 is this part of the thing, which is the frequency. All right, now to do this, we had to import from operator, we had to import this item getter function, which we use to great effect here. But there's a general and generic way to do this without any other optional modules. And I believe I mentioned this before I left last week. We had a brief conversation about the lambda function, the use of an anonymous function. Well, let's take a look at that. So in most languages, or in many languages, there's this concept of a use once anonymous function, a function that you create just to pass as an argument, or a function that you recreate just as an optional argument to sort, for example, that you're going to create and use in one place, and then you'll never use it again. It's specific and custom for just this one use. And when you do that, sure, you could define the function as part of your file and then invoke it. But that leaves that function hanging around for others to use, or maybe to sort of mess things up for you later on when you reuse the name of the function, for example. It is nice to be able to have a function you can use once and never have to worry about it hanging around and messing you up. So they are applied like any other function. The syntax looks a little bit differently because you define it in line and then pass it into a function to be used. But we're going to pass, instead of the function name, we're going to pass the whole definition around. So it's this package. And these go by different names. You'll see them called lambda functions. You'll see them called continuations in some contexts. So there are a lot of different names that you'll see for this same idea. In Python, this is called a lambda function, and you can see that my item getter thing has been replaced by this funny expression right here, lambda x colon x1. So what does this lambda function do? Well, this expression describes a function that has no name, so hence lambda, which is anonymous. It is a function of one argument, here x. So this is like saying def anonymous function parameter x. So this is the parameter, the argument to lambda function. And it returns x1. So there's no explicit return here. An anonymous function always returns something, otherwise it would have no use, right? It's there to do something, to access something and return something. So this anonymous function takes a single parameter x and returns, assuming that x is a structure that can be indexed, assumes the second element, x1. Notice how this lambda fills exactly the same location as this item getter 1 does, right? It is essentially a cruder version of item getter. It says, apply this anonymous function to every element, this tuple, when you sort it. It's the key that you're sorting by will be whatever this anonymous function returns when it's applied to each item. And this anonymous function, when x is a tuple like this, will return that frequency. So the anonymous function is a way of building an index expression, for example, that is used once only when I invoke sorted. This is the only time you'll ever see this used. But of course, within sorted, it's going to be used a lot, right? Because if I'm sorting a list of 500,000 words, I'm going to be using it approximately order n log n times to access the parts of the word I'm sorting by. We can use lambda functions for some other more advanced concepts. They can be really useful and sometimes a little bit confusing. So let me show you an example. I might define a lambda expression that defines an anonymous function on the fly. So here's a function description. This is def make incrementer. This is a normal function, Python function, a new one, make incrementer. It takes a certain argument, n, which is a number. And this function, here you're seeing the inline form of the function. We would normally type it with a carriage return indent, but it's the same thing. So make incrementer n returns a lambda expression. This lambda expression is a function. So this function returns as its value a function. So make incrementer is a function that returns a new function that's anonymous, and the new function is defined on the fly depending on the input parameter n. This is like all kind of smoke and mirrors, but think about it. This function, if I call make incrementer of 5, this function that is returned will always add 5 to whatever its parameter is in the future. So here's an example of invoking make incrementer. It returns this lambda expression, which I see as just a function. So a function without a name. If I take this function without a name, remember, make incrementer 4, evaluated left to right, is this function, and I pass it an argument 5, then this make incrementer 4 applied to the argument 5 will return. Anybody want to guess? Make incrementer 4 returns a function that adds 4 to its argument. So this function is, you can think of this function as add 4, and you give it a value 5 as its argument, this is going to return a 9. So this thing here, if you look at this weird line with the 2 parentheses, this part right here is the thing that's evaluated first by the Python rules. It returns a function name, actually a function definition, which then is applied to one parameter, the 5, and returns 9. Make incrementer 10 of 5 creates a new function, an anonymous function that adds 10 to its argument, so this one will return 15. So I can write functions that are given parameters, generate new functions that incorporate those parameters and do something interesting. So I've written, by being able to pass around lambda expressions, I've built functions that define other functions on the fly. So this stuff can be a little bit hard to understand because it's a lot like recursion in a way, except here I'm actually creating functions on the fly that I invoke on new parameters, and that function that I've created might itself create new functions on the fly. So you can see where this is going. So it's a little bit hard to understand. It is not something you should be using every day, but there are situations where this capacity is incredibly useful. In particular, for example, when you're writing a compiler for a programming language, doing this kind of stuff is really run-of-the-mill, and it makes your life a lot easier. Okay, so where were we? We wanted to find the top k most frequently used words from each book. We defined this function. We built this list. We returned the list sorted in reverse order based on a lambda expression that identified the frequency as the thing I'm sorting by, and then I returned the 0 through k elements of that. Okay, a couple of problems. Does this work? Absolutely it works. We've actually come a long way in a short time. We can get the 20 most frequently used words. They won't include words that are too short, so probably have reasonable words. The problem is it seems a shame to take all 25,000 words in Treasure Island and sort them just to find out what the 20 most frequently used ones are. Right? Think about it. We've talked about sorting before. Sorting in the best case is order n log n. 24,000 times the logarithm of 24,000 is still a lot of work just to find the 20 most frequently used ones. Seems to me we should have a way of being able to find the top 20 without sorting all of the other words. We really don't care whether the 21st word is X or whether the 21st word is Y. We just want to know what the top 20 are. So why do we have to sort all the words? So this is where thinking a little bit about algorithms can pay off in a really big way. We studied in class selection sort. Remember how selection sort worked? Who remembers selection sort? Anybody know how it works? Can you give me a short description? Remember the cards? And I would scan, and what would I do? Each iteration, what would I do? Anybody remember? Go ahead, Ben. Okay, so I'd find the minimum value, or in this case, the maximum card, the highest card, and move it to the first position. In the second scan, I would start one over because I've already got the highest card. I'd scan it and find the next highest and put it in position. Well, it stands to reason if you do this, if you just do the 20 first passes, you will have identified the 20 largest or most frequently occurring words. And you can just abandon selection sort after it's sorted the first 20 elements. So here's our selection sort. Takes a list. And what we did is We let I range from length of L minus 1 up to length of L minus 1. Remember, the last time through, you don't have to worry about it because the last element will always be in sorted order. I find the index j, which is I plus the rest of the index of the minimum value of the rest of the list in the rest of the list. So this gives me the offset plus the index. That's j. I exchange them, and I do this order n times to sort it. But here I'm just going to change it. I'm just going to do this k times instead. So here's my new code. This is exactly like selection sort, except that I'm only going up to k elements. And then I do the swap, and I return the top k elements of L. And that'll return the list of the tuples word, comma, frequency for the top k words. How much work are we doing? Well, we're doing about k times w work. Selection sort, you may recall, was order n squared. It wasn't an optimal sorting algorithm, so it did work in order n times n. But here we're doing k times however many words we have. That's our n. So we're doing k times w. And for a piece of a work like War and Peace with 500,000 words in it, 20 times 500,000 is really basically 500,000 words, order 500,000. So it's much, much better than sorting all of War and Peace, which is 500,000 squared work. I'm basically doing 500,000 work, saving myself 500,000 times of effort. Does everybody understand that? It's kind of important because it shows when you think a little bit about what it is you're trying to do rather than just writing the code. If you spend a little bit of time thinking about, is this the right algorithm to use? Ideas like using snippets of other algorithms you've studied can really improve performance of the code. I had a conversation with somebody on Wednesday, I don't remember who it was, leaving class. Was it Kyle? Is he here? May have been. About why use dictionaries in the first place? So much easier to use lists or arrays than dictionaries. And the answer is, dictionaries are enormously more efficient than some of the other structures like that you may have used in the past, right? Because when I add something to a dictionary, that's an order one operation. It's a constant time operation. So dictionaries give us a huge advantage in efficiency, and it's one of the really great features of Python is that it has these dictionaries built in. In other languages, they're generally called associative arrays, and not every language has them. So having a dictionary can be a huge win from an efficiency perspective. All right, the second issue is, you recall that the whole point of doing this top K seems weird that I would first create this dictionary of word frequency values and then turn it into a list. So I have the dictionary already, I want to turn it into a list that then I can sort. That seems like kind of turning a square peg into a round peg just so you can stick it into the sorting function. Wouldn't it make more sense to rewrite parse in the first place? This is the function that created that dictionary. Wouldn't it make more sense to rewrite that function and maintain a list of word frequency pairs in that list to start with? Right? Why go to the trouble of building the dictionary only to turn it into a list of word frequency pairs? Well, let's see if that makes sense. Recall that War and Peace had 25,000 words, and those unique words, and those were taken from this 500,000 words in the book. So every time I add or update, as I scan through these words in the book, every time I add something or update something in the dictionary, that's a constant time order one operation. Doesn't matter how big the dictionary is, the cost of adding one to and finding an element and adding one to it will always be the same. Right? That's kind of the magic of dictionaries. So building this dictionary in parse is essentially order n works. I scan all the words in the book. For every word, I do a constant amount of work. So the cost of building the dictionary is essentially related proportionally to the length of the book in words. Period. Only that. Converting that dictionary to a list requires order number of words work. So the building of the dictionary cost me this much work. Building the list out of the dictionary cost me this much work because it's based on unique words. And extracting the top k elements of that list, we've already seen is w times k, but since w is so big with respect to k, that's also essentially order w work. So by our little algebra of runtimes, we do order n amount of work plus order w amount of work plus order w amount of work. So these are sequential things. First you build a dictionary, then you convert it to a list, then you extract the top k items. And we know when you're doing things in sequence, you look for the dominating cost. So order w and order w are the same. Order n is much bigger than order w. So all of this work is done in essentially the time it takes to read the book into Python. Open a file, read it in, all of this stuff you get essentially for free. In contrast, if I had an unsorted list of word frequency sublists or tuples you can't modify, so it'd have to be a list of lists, it would require every time I read in a word from the book, I'd have to scan that list, which takes order w work, to find the right sublist to add one to the frequency. It's just a serial scan every time. So that makes order n times w plus order w work, and not, as it is up here, order n plus order w work. So this idea of keeping word frequency sublists and maintaining those is really much less efficient. It's a huge cost. Now you might say, that's stupid. Why would you keep these in an unordered list? I could maintain this list of word frequency sublists in some order, right? I could keep them in alphabetical order, for example. But I would have to do a little bit of work to maintain them in that order. And even if I had binary search, it helps a little bit because instead of order n times w work, it's order n times the logarithm of w. But order n times the logarithm of w is still more than the order n we get with the dictionary approach. So thinking about the algorithm, thinking about the data structure, that's what makes you a computer scientist and not just a programmer. Right? These kinds of arguments should always be going through your head. Is this the right way to approach the problem? Is there a more clever, a better way to approach the problem that will pay off in efficiency? And you might say computers are fast enough today that doesn't really matter, but the point of algorithmic analysis is it always matters because there's always a problem that's large enough where you're going to see what you choose may not be the best solution. So we did the right thing. We built a dictionary, and while it looks like we just threw it away by converting it to a list, the cost in algorithmic runtime is clearly the right choice. So we're really at order n work for doing all this sort of counting and frequency analysis and extracting the top k words, and that's pretty cool. All right, so let's take a look at War and Peace. We still have some problems with punctuation. We still have problems with dealing with stop words. We haven't even talked about the problems of punctuation that occurs within a word. And then, even then, there's other types of problems like different forms of the same word meaning that we would like to unify. So let's just take these a little bit at a time. So we need to do better with punctuation, and we're going to build what's called a stemmer. So let's talk first about punctuation and contractions. So for example, I go to Wikipedia and I look at the list of English contractions. Contractions are an interesting case where punctuation is used to change the orthography of the word. So when I say didn't, it's just did not, right? And it's the extra apostrophe and reduced by 1. And what I could do is if I had a list of stop words, which you can also get from Wikipedia, and I had a list of the common contractions, what I could do is I could make a pre-pass through War and Peace, removing stop words and replacing all the contractions with their expanded form. So didn't would become did not throughout the book, and then I would be done with having the contractions with the apostrophe within the word. So we're going to take this approach to removing contractions and punctuation. What we're going to do is we're going to build this list of this tuple of contractions and expanded version equivalences. So from that Wikipedia list, I see that aren't is are not, can't is cannot, couldn't is could not, couldn't of is could not have, and so on. And then you can see there's a whole bunch of these, even down to the fact that maybe we might want to get rid of hyphens in words and just replace them with spaces. Okay? 92 substitutions on the Wikipedia page, not that many. So what we're going to do is we're going to modify that initial parse function, which you recall is the one that opened up the file, read in each line, and we called parse on each line. And what it would do is it split the words up. It would maintain the frequency count in the dictionary. And we're going to use a replace command in that string to replace any contractions with their expanded form before we count the word frequency. So here it is. It's just as before. There's my dictionary. Open the file. And now for every line in the file, before I parse it, I'm going to consider every tuple in that contraction list, and I'm going to replace x with y in that list. So there's this inner loop which repeats 92 times because there's 92 contractions I want to remove. And I'm going to replace the contraction form with its fully expanded form 92 times. And then I parse the line, and then I go on to the next line. So it's a small change in the code. Not particularly efficient because I'm going to do 92 string replaces, most of which won't do anything because it's not like every line has a contraction. They're relatively infrequent, which is why I can get away with this. Relatively few replacements actually occur. Almost works. So here is my dictionary D, which I get from inputting War and Peace. And if I look for the word isn't with the contraction form in my old version, I find there are 47 instances of isn't in War and Peace. It's not even that many. See, the contractions are few. With my new version where I do the substitution, it turns out that it got rid of most of these, but there are still 19 isn'ts left. That seems a little bit weird because I've replaced isn't in every line in the file. Every line as I read it in, I do the replacement. So how come I miss 19 of those? Anybody have an idea why we miss 19? Oops. Why did we miss? Where did these come from? Keep in mind what order we do these things in. For every line, I replace the contractions, and then I parse the line. Yes, go ahead.
If there's a contraction that has punctuation directly after it.
So if the word has punctuation directly after it, turns out that string replace doesn't see the punctuation that's outside the word. So if the last word in the sentence were isn't, period, that would still be okay for this replace method. It would still replace it with is not, period. So we'd be good. But there's something else going on here. Anybody? Yeah, in the back. So it could be that a word gets split over two lines. Could be. But we're reading line by line, and if I have the word in the dictionary, it wasn't split over two lines because it occurred within the line. This has to do with the order in which we apply the operations. Remember what does parse do? This is the thing that takes the line and splits it into words and turns in each word into lowercase. So what turns out here is these 19 words are all the first word in a sentence. So if the sentence starts with the word isn't, the I will be capitalized, and this replacement doesn't see that word as being the same. So because we're doing the replacement before we lowercase stuff, we're going to miss some words. So I can lower the case earlier, promote the lowering the case earlier into my code so it doesn't wait until I'm parsing the line. I could read in each line and reset it to its lowercase version, removing all punctuation, do my replacements, parse the line, which now no longer needs to do the lowercasing, and return the dictionary. And I'll see that all of those words will be done. All those isms will be done. Now, is it a good idea to get rid of capital words? So remember I said that one of the things we want to do is figure out who the characters are in War and Peace. And one of the ways we do that, ways you identify a character in a book, is if it's a proper noun, and a proper noun is capitalized. So if all those names now become lowercase words, it's a little bit hard to tell that those words mean a name. And if you can't tell it's a name, how do you know it's a character? So you can start to see how complicated dealing with text is. We were trying to identify characters based on strictly syntactical cues, a word that appears in uppercase all the time. And when I've done this in the past and other related projects for this class, we once took the Iliad and the Odyssey in English translation and identified all the characters and built a really nice character map of these two large Greek, what's the word I'm looking for? Epics, yes, thank you. It worked fine, except that words like Athens showed up as characters, which isn't really what we wanted, because Athens is a city, proper name, but it's hardly a character in the book, right, in a real sense. What makes a character is an element that is proper name, that's an object in the world, that has intention and that acts. And you can't tell that from the syntax of the text. So ideally, we want to be able to analyze also the sentence structure and see when a proper noun is used in a way that it actually has intentionality. Then we might be able to identify characters more specifically. So this stuff gets really complicated really fast. We're going to do things the dumb and easy way to start with. So here's my new read input where I lower the case. I'm going to forget about characters for a minute. And I'm going to add this stemmer step here, which I will talk about, I think, next time. So we've got our new parse function, which is the same as it was before, except that we're stripping the punctuation here, but lowering the case in the reading part. So before we get here, we've already lowered case. What we haven't talked about is this part. And this stemmer here addresses another similar issue like the part about identifying characters. And that is that when I'm identifying things like verbs, verbs appear in many different forms. I would like, if I'm trying to build some sort of sense of what's going on in the story, if I see the word find, and I see the word finding, and I see the word found, I'd like to identify those words as all being sort of the same kind of word. They're different variants of a word that has a single meaning, right? It's an action to find, found, finding. And that applies for all sorts of words. And some of these are really easy. So a word like cough and coughing, it's easy to tell that those two are related. And that's the job of this stemmer. The job of this stemmer is to use the syntax of the writing in English to identify parts of the word, generally the ending part of the word, that is less related to the meaning of the word, but more related to how the word is used, and strip those away, just like it was useless punctuation, to get to the root or stem of the word. So now all of a sudden I've raised my sights here. I want to be able to find not just the frequency of words, but the frequencies of these stems that are sort of indicative of a whole class of things that are identical. So found, find, and finding, and so on. Okay? We'll pick up with this next time. This is one approach. It's purely syntax. We will probably spend a little bit of time later looking at ways to do this with more sophisticated tools. All right, so we'll cancel lab for tomorrow. Have a nice break.